this trick will always hold good. It will be safe to count them separately and simply add the two. So, for those who like to think pictorially, this is the kind of picture, oops, let's give it a white background. This is the kind of picture you might have in your head, a very simple picture. Okay, so we've got a set S, and okay, I've chosen some particular predicate, it makes it look like it's half and half. You know, not necessarily. I could choose a completely different splitting like that, and I could count the bits above and the bits below. So I can choose any predicate division I like, and I can count the elements on one side, which do satisfy the predicate, and then separately count one on the other side, and I can add the two together, and I will get the right answer. Okay, so how do I know I will get the right answer? Well, I can justify it using the laws of logic, the laws of the excluded limit. How could it be that I would get the wrong answer? Well, either I will miss something out, so I will get a number that's too small, or I'll mistakenly count something twice, so I'll get a number that's too big. But let's think what it would mean. How can it be that I miss something out? Px, or not Px, is always true. So every element will be included either here or here. I won't count something out. And similarly, how can it be I count something twice? I won't, because Px and not Px is always false. So I won't include an element both here and here. So that's a simple logical justification of this little principle or rule. Okay, the next idea that's important is that of two sets being disjoint. And we've just seen an example of that, this little partitioning where we don't have any elements in common. And we've now split it, and there's no overlap, there's no confusion. That's a particular example of what we call disjoint sets. It's just a jargon way of saying that here are two sets, and they don't have any elements, members, in common. So an example that's familiar to you, if we take the sets of odd numbers and even numbers, they are disjoint. There is no number that is both odd and even. And more generally, if we have any set S and its complement, S prime, they are disjoint. There is no member that belongs both to S and S complement. So how can we write that down? How can we write down, using the operators that we already have, that two sets are disjoint? Perhaps we need a new notation to be able to say that. Well, we're back in the same kind of territory as we were when we looked at the idea of logical equivalence. There may be many different looking formulae, but they are actually saying the same thing. So here's a little bit of practice for you. And there's a two-stage business going on here. So the first stage is you might like to check that you agree, just informally, that all of these four things are all expressing the same relationship between sets P and Q. And to help you along, particularly those of you who like to think pictorially, here is a picture corresponding to situation. Let's try and make this just a little bit tidier. Okay. So, might make it tiny in a moment. This is really persevere. Bear with me. There we go. Slightly better. Okay. So, there it is. Discuss with your neighbour then. Do you agree that what we see on the left there are four different ways of expressing the same situation, namely the one that I've depicted over here in the Venn diagram? So just take a break, first to discuss that, and then secondly, this rather frightening, or more frightening question. Suppose, and don't worry, I'm not going to, suppose I would say to you, okay, now prove it. That is to say, Now prove that each of these four things all actually says the same. Whoa, okay, there's four different things and they're all equations about sets, and then well, actually this one is an inclusion, and then I've got to show they're all saying the same thing. Gosh, how would I organise a proof like that? So that clearly is a bit of a harder question. So two-stage, the good news is, either way, you get a break from me again. So do that. First, check that you agree, just the intuition, that these statements are all describing this situation in the diagram. And secondly, the tough one, how would you organise or structure a proof that they really are all saying the same thing? Go.
Break them down into the other things in different sections.
All the space outside.
Is it working?
Yeah, it is. It is kind of.
I'm so tired.
I would just read C. I would just read C.
C is the one that makes most sense.
I think it's D doesn't make sense.
It's a weird way to say it.
Everything is real life.
What a brilliant article. It's a good article.
The second one was about
Find it. I thought I was download the app again.
the third one was about C.
That was
the C. What you need to do is use the Fibonacci series.
You need to really focus.
That's fun.
That takes a picture.